And put that over here. Okay, so we left off on Monday with the introduction to MRI. And the signal from which we're going to make these pictures is a radio frequency signal that's emitted by the patient. After we stimulate the patient with radio frequency energy, we get RF back. And there is a linear relationship between the frequency of that radio frequency energy, omega, and the magnetic field. So at 1.5 Tesla, which was the standard field strength for many years, that corresponds to 64 megahertz, which is somewhere, I forget where it is. It's just like off one end of your FM dial, right? So if you guys never listen to FM radio, I guess, because you just listen to podcasts and what else. But it used to be in a car, you had a dial to tune your radio. And I'm not sure if those exist anymore, but just off to the left side of the FM dial was this frequency here. So one of the things you need to do when you're sighting an MRI scanner is you need to put it actually in a Faraday cage or an RF shielded box. So the whole room has walls that have either copper behind them that are all sealed up with really good welds. And if there's glass, the glass has to have some kind of permeated conductor in it so that RF can't get in or out. If you don't do that, when you make your picture, you're going to get all this noise, RF noise from the environment. And so it adds to the expense of sighting a MR scanner and the time. Because the companies that build these RF enclosures are not common. So anyway, at 1.5 Tesla, we'll be working at 64 megahertz. 3 Tesla, because of this linear relationship, we'll be working at 128 megahertz. The relationship between frequency and field strength is dependent on which nucleus you are imaging. We image protons mostly, and so this gyromagnetic ratio is for protons. You can image other species such as carbon. You can image phosphorus, things like that. And the problem with imaging those things is they're in such low abundance. The signal is very, very weak, but it does give you some biochemical information, which is, quite unique to MR. So any questions about that? Just if you have questions, just speak up so that we can address them. Okay, so here we are again with the magnetic field. And this is a radio frequency receiver coil strapped around this patient's, torso at this point. When the patient is rolled into the scanner, just inside the magnetic field windings is a thing called the transmit coil. And this provides the radio frequency energy that we're going to transmit into the patient. This design here is called a birdcage coil. And current runs through the elements along this Z direction, and creates a magnetic field inside the patient that in fact rotates. So you can think of a radio frequency field also as a magnetic field. If I have a vector here with its arrow tip pointing up, caused by current density running through these wires. As you can imagine, if I have, current going in a circle around this way, basically, so current going down this way and coming back up this way, I make a magnetic field pointing upwards. And then if what I can do is change the phase of the current in these rungs such that the magnetic field doesn't just point upwards, but starts to rotate. And it actually rotates in this transverse plane of the XY plane. And we can get it rotating at 64 megahertz by programming the current in these elements such that they're phase delayed. And you have these currents running around with this phase delay of 64 megahertz, and then the magnetic field rotates around. So that's one way to think of the transmitted radio frequency energy by this coil, which is called the transmit coil. That gives you a very uniform transmission field across the patient, which is good. And so we can generate a signal from the entire volume. You could also use this coil to receive the signal that's going to come back from the patient, but because the elements are far away from the material that's generating that signal, because this distance is pretty far, you lose a lot of intensity just by 1 over r squared, right? And so normally for the receiver part of this, you put loops of copper very close to the patient, or as close as possible. This coil also is designed to measure very small signals, and it has very strong preamplifiers locally right at the coil elements themselves. You could, have a design coil like this that also transmits, but the transmission would have intensity changes across the patient, and it would be quite inconvenient. So usually you transmit with this more uniform coil. The receiver coils can get pretty sophisticated in the sense that if you look at this experimental coil that came out of a lab in Boston, each one of these circles here represents a kind of independent coil element. It's connected with a preamp to some cable that the signal comes out, the electromotive force, the voltage that you measure inside this coil gets transmitted out here. It's overlapping with its neighboring coils such that the mutual inductance between these two things is, you try and minimize it so they don't excite each other. So you don't want, when this coil has a current running in it, because your sample is causing that, you don't want the coil itself to excite the coil next to it, right? You'd rather overlap these things such that mutual inductance gets canceled out. So there's some design considerations for how you place these coils around the patient. And as you can see, there's 32 coils here placed around the patient's brain. And so this is called a phased array coil. And this element really receives stuff just underneath that element only. It doesn't really receive much signal from, say, over here. And that's good in the sense that you want a match between the volume over which you're receiving signal, right, and the sensitivity of this coil, because both noise and signal come from the volume of the patient. When you turn on your receiver and you haven't done anything, you haven't stimulated any magnetic field changes or anything like that, and you just look at the voltage coming out of your coils, as soon as you start sampling it and look at the preamp, you basically, from this coil, you generate a random set of voltages, okay? And it's at a certain level that is partly due to the electronics, but mostly due to the patient. You're actually measuring sort of the thermal motions of charged stuff in the patient. And there's no way to really get rid of that noise source other than like deep freezing the patient, which you can't do, right? So the noise source for MRI is the patient. And interestingly, the noise source is across the entire spectrum of your image. It's not sort of a particular frequency. It's called white noise, right? It comes in at all frequencies. So to maximize your signal to noise, it's best to have a small coil locally picking up the signal here and picking up a small volume around that voxel, right? Okay, and then, this is the beta version of this coil that was built, say, 25 years ago. And then nowadays there's products that have all of these 32 channel coils up to, now I think you can get up to 128 channels, et cetera, on these modern imagers. Any questions about the RF coils? Okay, so the next set of coils we're going to become acquainted with are called gradient coils. And these, what these do is they produce a change in the static magnetic field. Remember, the static magnetic field from the windings in the big coil is in this direction. It goes along the bore of the scanner. We put the patient in there and they are bathed in this very strong magnetic field. And if you don't do anything, they're just sitting there in this large field, and you generate a magnetization in the patient. What we're going to do is we're going to change that field, that Z field, as a function of position in the bore. And the way we do that is by pulsing current in these auxiliary coils that are sitting around the patient. They are also in the cylindrical bore of the scanner. And so they have to sort of slip into that cylindrical bore and take up as least space as possible. There are 3 of them, usually. The Z coil, it changes the magnetic field as a function of Z. So I might have a higher field up here and a lower field down here. And then I have an X coil, which changes the field as a function of left to right position, right, and in the patient. And remember, it's a change in the Z field, right? And then the Y coil changes the Z field as a function of, the AP direction in the patient, or the Y direction. So those 3 coils are there, and what you do when you're programming an MRI scanner is you figure out how to pulse those coils in a really clever way to make the picture that you want to make. So it's all about programming those coils and the pulse. Excuse me for a second. I just got a notice about a patient in the scanner. Sorry, I did not remind you. Let's go back. Okay. Okay. All right. Okay, so let's move on. Here is a cartoon of the 3 gradient coils and where they are in the cylinder. So the magnetic field the coil windings are out here, and then inside those are the coil windings for these gradient coils. And they are connected up to an amplifier. And what the amplifier does is it provides current to these gradient coils in order to, make a magnetic field. We would like to switch these on and off very quickly. And so what that turns out to require is voltage changes, high voltage, and very fast changes in those voltages, and a lot of current, right, from this amplifier. You're switching it basically at audio frequencies, so it's sort of like an amplifier you would use like with an electric guitar or something like that. But a lot more current and a lot more power. So when we look at the amplitude of the gradients provided, the 5 Gauss per centimeter is sort of a typical maximum gradient. And so, basically you're changing half a Gauss in a millimeter, right? So it's a fairly steep change in the magnetic field as a function of position. But where these amplifiers are required is you want to change the magnetic field or change the gradient very quickly. And so most of these now switch at around 200 Tesla per meter per second. So this is the gradient that we would hit if we switch this amplifier on for 1 full second, which we don't. But you can get up to this 50 millitesla per meter in 250 microseconds. Okay, so that means we're sitting there with no gradient, and then 250 microseconds later, bang, we're at full gradient, right? And so that allows us great flexibility in how we're going to encode the signal from the patient. So these amplifiers now, when this was made, this was Tom Lu's slide back in 17, they're sort of a megawatt. And this is interesting, in the Metallica tour at that time, their total power for all the amps on stage was like 1/3 of a megawatt, right? So this thing could have, run the whole Metallica tour. So here again are cartoons for the current paths of gradient coils. And so here's the X, the Y, and the Z gradient. And then when they're all put one on top of the other, it looks something like this. They're all in there simultaneously. And so the question is, how do you pulse current in these loops to produce a change in the magnetic field? I think, okay, so let's look at a X gradient, for example. And so here's the X direction. So this is the Y direction. We're sitting at a constant Z value. If I have an X gradient, what that means is as I move away from the origin and move to a larger X value, so towards, say, the patient's left arm, and here we're moving towards the patient's right arm. As I move this way, the Z field, the magnetic field in the Z direction changes, goes up. And ideally, we would like to make that change a straight line, right? A linear change, right? Such that the magnetization over here, or the would be precessing, or the resonant condition for the NMR experiment over here would be at a slightly higher frequency, because we've changed the magnetic field. We've added we've added an additional magnetic field out there. Over here, we've subtracted some magnetic field off the static one, and therefore over here the spins or the sample or the patient will be at resonance at a lower frequency. So 64 megahertz right in the middle, and then out here we might have 64 megahertz plus some delta frequency, 64 megahertz minus some delta. So in order to create that change in magnetic field as a function of position, this is how these coils work. We pulse current in them, say in this direction, like along this arrow here. So my current is going around this element. There's 4 elements to this Y gradient coil. So this is the Y direction. And one of those elements, I have the current going in this direction, right? And then the other gradient coil of current is going in this direction, right? And we're turning on this path. The elements that are really providing the gradient in the patient that we're going to use is really this element and this element, okay? And if you ask, well, what's happening here? When the current rolls through here like this, if I use the right-hand rule and put my thumb across this line here, then I'll have a magnetic field going around like this, in that direction. Similarly, over here, the current is going through like this. Same right-hand rule, I have a magnetic field going around in this direction. And so at this point, I have an additive magnetic field in this direction, right, when I add those two up. I pulse the current such that down here, the current is going through this way. And now, if I put my thumb along here and use the right-hand rule for current in a wire, what magnetic field does it make? It makes a field that rotates around this way, right? And so that pushes the magnetic field change in this direction. Similarly, for this current here, put my thumb along this direction, and I get a magnetic field like this, and it changes the magnetic field in that direction. So the net effect is at the middle, I don't get a change. As I move up towards these current elements, I get a greater change in this direction. As I move down towards these elements, I get a greater change in this direction. And that provides this change as a function of Y in the magnetic field, and that's the Y gradient. These are called Golay coils. They were first designed for NMR spectrometers as shim coils, basically, to try and interactively make the field more uniform. But they were transformed into imaging gradient coils when MR imaging came along. These elements out here are just return paths for the current, and you would kind of like those to be very far away so that you don't interfere with your gradient over here. Any question about gradient coils and how they work? The Y or the X gradient coil is exactly like this. You just rotate this whole thing by 90 degrees. You take the cylinder, rotate it by 90 degrees, and you'll have a X gradient coil. In the Z gradient coil, we can go back to this picture, and this is a really trivial one. If I want the field to be higher as I go this direction, all I do is I put a if I want a larger field, well, let's do it in this direction. So if I go this way and I want the field to be higher over here, if I pulse a current in this loop going this way, it makes an additional magnetic field, so we're at the center of the loop going this way. And if I pulse this coil going in the opposite direction, right, it makes a field going in this direction. So over here, we subtract from the Z field. Over here, we add. In the middle, we don't do anything. These two effects cancel out. And so you get a linear gradient in Z just with two simple sort of circular turns of this coil. So that's a pretty easy one to make. So now, we turn to, so those are the gradient coils for changing the magnetic field as a function of position. And you can think of that as changing the resonant frequency as a function of position inside the scanner bore. That is how we're going to encode where spins are. We're going to encode them by changing their resonant frequency as a function of position. And we'll allow the magnetization vectors at that location to evolve at those different frequencies such that they generate phase shifts between themselves and some other voxel in the patient. Now we're going to look at this whole concept of the magnetization vector. And remember from last lecture, what I said was when you put a sample, let's say we have a sample here, it's a little voxel, in a magnetic field that's in the Z direction, we call that the static magnetic field, or B sub 0, B naught. The magnetization grows over time and hits a steady state value. It just sits there after a certain time, after a few seconds, right? For water, anyway. And this magnetization is parallel to the B naught direction. If we pulse a radio frequency pulse around that sample, what we can do is we can, in fact, rotate the magnetization vector away from the Z direction, such that it is now not pointed in the Z direction, but it has some component in the XY plane, okay? And what happens at this point is, because if I shut off my RF pulse that made this tip angle, after it's shut off, I have magnetization in the transverse plane, and it precesses around the static magnetic field. Left to its own devices, it just sits there and precesses around that field. And as I said last time, this is a bit of a fairy tale, the what is going on here, that we have this magnetization vector. This is in fact, protons undergoing a transition from the higher energy to lower energy states, and they're doing that in phase, causing a signal in your coil. But the really nice way of modeling it is adding them all up and calling them this magnetization vector, and then characterizing its precession in the transverse plane. The magnetization precesses at the Larmor frequency, right? So it precesses Remember, at 1.5 Tesla, we had 64 megahertz. So this thing processes around at 64 megahertz if its B naught is 1.5 Tesla. So it will process around in the transverse plane, and we can then further, using external RF, apply a magnetic field that tracks with it and cause it to rotate, either say further down to the negative Z direction if we use a higher degree pulse than this 90-degree pulse, which took us into the transverse plane. Say we use it as twice the amplitude, it will take us all the way down to the negative Z axis. And then actually we don't have anything processing in the transverse plane at that time. We just have this thing recovering back along Z, and that's called an inversion pulse. If we look at what happens after we apply a radio frequency pulse that rotates the magnetization vector down into the transverse plane, we will get regrowth of the Z component of the magnetization over time. And basically, we've taken it from its steady state value down to 0, and then it's going to grow back to its steady state value at a characteristic rate, right? And the rate itself is what determines that characteristic rate. Usually it's sort of the thermal properties of the stuff that's in the sample. So however the water is contained, if it's in liquid state and it's a body temperature, the magnetization will get back to its equilibrium value at a specific rate, and that rate is called T1. You can model this growth from 0 back to the equilibrium value as this function here, which is just a mono-exponential growth towards some baseline value. And it's characterized by a time constant, which is called T1, right? So a T1 of 500 milliseconds, means at 500 milliseconds, you have 1 minus e to the minus 1 towards your recovery, right? Which is 63% M naught. So this is the T1 constant time. So when I was describing it before, I said it takes a couple of seconds for water basically to come to equilibrium. That's about right. Pure water probably takes about 2 or 3 seconds. Blood, because it has large molecules in it and stuff, it recovers more quickly, as does water and muscle tissue and stuff like that. When we look at what's happening in the transverse plane, the magnetization vector in the transverse plane decays away more quickly. So we see a rapid decay of the signal in the transverse plane. So as this thing is precessing around, we can see it generating a voltage in our coil that's sinusoidal, and this frequency here is at the Larmor frequency. And the amplitude is decaying away, right? This is an independent decay from what we just looked at, from this growth. Okay, this growth occurs on these time constants, like 500 milliseconds. The T2, this is called T2 decay, is usually much faster. There are some materials in which the two constants are roughly similar, like absolute clean, pure water. You'll have a very long T2 decay. But in biological tissues, the T2 decay is usually pretty short. And so we can measure signal for as long as this signal is available. And the T2 time constant is kind of the fundamental limit to that. This gray curve underneath here shows the fundamental T2 decay of this substance. The red curve shows an even faster decay, which is called T2 star. And the reason this faster decay occurs is because the sample is usually not in a perfectly uniform magnetic field. And so the magnetization vectors from point to point are precessing at slightly different frequencies, and therefore they don't add up coherently for as long as they could, right? There's this basically T2 relaxation where the magnitude of the magnetization is decaying away regardless of what the magnetic field looked like. And then this faster decay, which is if your sample is in a magnetic field that changes as a function of position. We can recover this more rapid decay. So if we look at the magnetization, we tip it into the transverse plane, it starts to break into different phases in the transverse plane because different parts of the magnetization are processing at different frequencies. What you can do is take the entire, if you think of this as sort of half of a pie or something like that, you can take the entire thing, apply a magnetic field for a very brief time as an RF pulse, and flip all of the magnetization vectors from their current phase position and reflect it such that they're in the opposite phase position. And what happens then is the ones that gained phase before that flip now are behind, and the ones that were behind when you flip them over, they're now ahead in this decay. And so what happens is they all come back together at 2 times whatever you chose to do this RF pulse here. And so now you have them all back together and you get this, it's called a spin echo, where the signal comes back. And so this is our first RF pulse sequence that we're going to look at, where we have a 90-degree pulse. We provide the radio frequency energy to the patient with that transmit coil here. We see the T2 star decay of our signal. The magnetization vectors all dephasing in the plane here. And then if we apply one of these 180-degree refocusing pulses at twice this time, we will see that signal come back briefly and then go back again. So this is like the T2 star decay on either side, but the height here is the true T2 decay. So this is called a spin echo. And for many, many years at the beginning of MR, because things had to move more slowly, like switching gradients and things like that, this was the pulse sequence of choice because it gave you a fairly long period of time in order to encode, switch your gradients on and get everything going. Nowadays, I would say most of MR imaging is done on this signal right here, right? You just do an RF pulse and then you start imaging right here. And because you can get everything done very quickly over here, you don't have to wait to get over here. Also, each one of these radio frequency pulses requires injecting RF energy into the patient, which can turn out to heat up the patient, especially if you make these time values short. So you do a 90 and then you pull this 180 really close, and you do that over and over again, you can start heating the patient up with radio frequency energy. So normally there's a program on the scanner that will compute how much RF, how many watts you're depositing into the patient. And if you try and prescribe a sequence that puts too many, it will tell you, you can't do that. You have to back off and do fewer pulses. So now we have these 2 time constants. The first one that we talked about was T1, which is how the magnetization comes back from 0 to its steady state value. And the T2 time constant, which is how quickly the magnetization vector decays in the transverse plane. Typical values, they range a lot, but T1 can be anywhere from, tens of milliseconds for really weird materials up to seconds. But in muscle, it's around 500 milliseconds, something like that. And T2 in muscle is around 50 milliseconds. In cerebral spinal fluid, both of these are really much longer than that. And this is what generates contrast in MR images, is that different tissues have different T1 and T2 values. And so we can generate brightness in, say, things that have long T2, or we can generate, brightness in things that have short T1. So if you have short T1, you come back to a higher signal more quickly. And then if we choose to apply a radio frequency pulse like right here, this tissue will show up bright because you get more signal from it than you do from this tissue. So let's look at this is our first pulse sequence in which we're going to show the gradients and the RF that we're going to use and our signal. Okay, so here's our radio frequency pulse. We're going to turn on a gradient, a magnetic field gradient in the Z direction during application of this radio frequency pulse. And what that does is, at a specific Z value, you will be on resonance, and those magnetization vectors in that plane will see this as a resonant pulse. The ones at higher Z values will not be at the right frequency. Their resonant frequency will be too high. And the ones at the lower Z values, their frequency will be too low. And so they won't get affected by this pulse either. And so what that does is this little gradient RF pair here creates a single slice in the patient that will emit signal. And so we're already very well spatially encoded because all of the signal is coming from a single slice after this pulse. Here's the signal, right? We see this free induction decay. If we turn on our receiver coil, we'll see this signal coming in. It's coming in at the Larmor frequency, or 64 megahertz, if we're at 1.5 T. And it's called the free induction decay, or FID. What we'll do now is we'll pulse the Y gradient briefly with some amplitude. And what that pulse is going to do is it will change the magnetic field as a function of position in Y by a certain amount, depending on the amplitude of this gradient. And the magnetization vectors that have positive Y value will precess or have higher frequency for this duration, and they'll get ahead in phase than the magnetization vectors at the center. And magnetization vectors below the center will have a lower frequency, and so their phase will lag behind. And so with this simple pulse, we will encode the Y location of magnetization vectors by looking up and down a column of the slice that we've excited. And we'll see that at the top of the column, the magnetization vectors were going faster, and so they're ahead in phase. At the bottom of the column, they were going slower, so they're behind in phase. And that's called a phase encoding pulse. We're going to apply a phase encoding pulse multiple times to the same slice, but with separate acquisitions, and add all those up. And then, since our signal decayed away so quickly here, we still have transverse magnetization. And so these gradients are still working to encode. Even though signal looks like it's gone, the magnetization is there. They're just out of phase. We apply a 180-degree pulse here in the same slice. We don't have to do that. I mean, but oftentimes you just apply it in the same slice with slice selection. And then we look at twice that interval, which is over here, and we get a spin echo. Okay. And that spin echo, as those magnetization vectors come together to make that spin echo, when they come together, they still will have the phase shift that we encoded over here at this time point here, right? And during this readout of this signal, we will turn on a gradient in the X direction while we're reading the signal out. And what this does is it makes things on the left side of the patient resonate at a different frequency than the middle, and different frequency than things on the right side of the patient. So we encode in real time by the frequency that the magnetization vectors are processing at the time we're sampling. We encode the X position of those magnetization vectors. So at this point, their Y location is encoded by a phase shift as a function of Y, and their X position is encoded by the frequency that we're seeing during the readout with this X gradient on, okay? So that is the quintessential, simplest, MRI pulse sequence you can think of. And pulse sequence programming languages were designed by each manufacturer such that you as a research person could swap this out for whatever you wanted, swap this out for whatever you wanted. You could make this thing do, within reason, virtually anything. And it became a huge cottage industry. It was just creating new pulse sequences that created different contrast. So if I have a magnetization vector that's, resonating at this frequency, it's going in the transverse plane. Obviously, this is idealized in that it's not decaying over time, but it's, rotating around. And then there's one that's at a slightly lower frequency here. When you add those up, you get the sum of this one and this one, this magnetization vector and this one. And encoded in this sum are these two frequencies, right? So this is what we're going to measure in our coil if we only had two magnetization vectors, right? And we would have to look at this signal and decode where it came from, right? The other way of encoding, which I alluded to in the Y direction in that pulse sequence, was phase shifts. So what we can do is, if I acquire one acquisition and I look at my magnetization vector, say it's off center in Y, and for my first acquisition, I do not use a Y gradient. I set this thing to 0, right? So we make an acquisition, set this to 0, and ask, well, what is the phase shift of my signal in Y? And it's obviously 0, right? It basically, I didn't apply a gradient, so I've got 0 phase shift at the beginning. And then I do another acquisition, second acquisition, in which I pulse this gradient and ask, well, when I'm reading out over here for this magnetization vector, what does it look like? Well, it starts with a phase shift, right? And so you can see it's shifted for the whole thing. And that phase shift is proportional to the displacement in Y times the gradient in Y, right? And so that's how we're going to encode the Y position. So the fact that we can encode with phase shift is why we can encode at very high spatial resolution with radiation that has a wavelength of meters, right? So it's not like optical microscopy where you're looking at, sort of the brightness as a function of position and your resolution is limited by wavelength. Here, our resolution is just limited by how finely we can measure a phase shift, which is pretty darn fine. Right? So you can get down to very, very small spatial dimensions when all you have to do is measure a phase shift between one acquisition and the next. Okay. So it turns out, and I'm not sure we're going to do it in great detail how this happens, but here's a mapping of magnetization vectors as a function of position in the XY plane. okay? And you can see that some of these magnetization vectors give off a very bright signal, especially those for this pulse sequence that are in pure water. And this is cerebral spinal fluid, so that's essentially pure water. And you get a very bright signal there. And then there's two other species in the brain that are of interest. One is gray matter and white matter. And you can see that the white matter tracks in this brain down through here are darker than these gray matter volumes here. And then this white bright signal is sort of cerebral spinal fluid that is bathing the brain. So this is our set of magnetization vectors, okay, that we're imaging, or this is the final image. And what actually happens with that pulse sequence, what it produces for us, is this thing. This is the signal we measure. And this turns out to be the Fourier transform of this thing. So you take this thing and you look at it and you say, what's its Fourier transform here? This is the raw data that you're going to collect. And I know that sounds a little magical, but we'll perhaps get to the point where we understand that just by looking at a little bit of simple math. This direction is normally the direction in which the X gradient is on, and so you collect signal along this direction. So this is, say, a set of 256 rows, and each row is a collected signal, right? And that's when the X gradient is on. And then we do that again with the X gradient on this way, but we have changed the amplitude of that pulsed Y gradient. So it changes the nature of the signal that we sample. And then when we put it all together, it turns out that all we have to do is take the inverse Fourier transform to get here. And as you might imagine, you know, if I have this set of magnetization vectors here, and this is the Fourier transform, this is our raw data. If I decided I was going to take a subset of that raw data and only image this much, right? When I take the inverse Fourier transform, I get a pretty good picture. You know, I took maybe 1/10 of the data here. It's a pretty good picture, but a lot of artifacts and blurriness because I'm missing a lot of raw data at the high frequencies of the Fourier transform or the Fourier space. But how we go into the Fourier space and sample all of this is essentially the major design criterion for determining what your pulse sequence is doing. There's another source of contrast, which is quite interesting in cardiovascular imaging, and that is the fact that some of the magnetization vectors that get affected by your first 90-degree pulse with remember we have this slice gradient. So we do a 90-degree pulse and it excites signal from a slice through the patient, right? So we get an FID from that signal, but we're going to image over here with a spin echo. And so by the time we get around to here and we do a 180-degree pulse in order to generate this spin echo, right? If this is a blood vessel, the blood that I originally excited with a 90-degree pulse, when I go to hit or I use a 180-degree pulse, that blood's already down here. So it's moved out of the slice, right? So all of the tissues that are here, right, they'll have, you know, the free induction decay here, and then these will generate a spin echo, and these will generate a spin echo. This stuff, not so much, right? Because it did not see the first 90-degree pulse. And so it is not going to generate a spin echo. And what happens is it looks like it's called black blood imaging. So here is the descending aorta, and we have virtually no signal from the descending aorta. Not because the time constants like T1 and T2 would give you no signal. It's because the blood just isn't there when you do the 180-degree pulse. So you get this really nice contrast mechanism, because now you can see what is vessel wall and versus blood, because all the blood is washed away. That's called black blood imaging. And then another opposite source of contrast is bright blood imaging, where instead of doing a 180-degree pulse, if we do very rapid sequential pulses to generate signal from this slice. And so we slice select, and the phase encoding isn't shown here, but we do a phase encode pulse here, and then we read out here, and then we do it again very quickly. Those, a pulse sequence that looks like that, sometimes these are literally 2 milliseconds apart, sometimes 1 millisecond apart. So you can do this really fast. And so we get signal from the whole slice at this point. And then when we go to acquire signal again from this slice, after only a few milliseconds, what happens is this stuff, this tissue here, because it's seen two RF pulses in a row, becomes saturated. We haven't let it recover by T1 recovery enough such that we generate a high signal here. However, what's happened here is new magnetization vectors, entirely new ones, have moved into the slice between here and here. And so when I hit it with this alpha pulse, I'll get a very bright signal from this stuff, even though I'm getting low signal from this stuff. And then you get the opposite contrast mechanism, where we see this bright signal coming into the slice from outside the slice. And it generates the good contrast between the blood and the background. This is just demonstrating at extremely high spatial resolution. This is, a tiny slice of the brain. And if you look at the details we've got here, what's going on here is non-motion corrected versus motion corrected data. And, when the brain is pulsing, if you don't cardiac gate, for instance, then these tiny little vessels here and tiny little vessel there, and the structures will be in slightly different configurations because of the very small displacement caused by the blood pressure that comes into your brain every systole, right? So it's cyclical. So if you cardiac gate such that you get it at the same phase every time, then it goes back to this really crystal clear signal. So as I was saying before, as your spatial resolution goes up, you basically have to motion correct everything or take it into account. But look at the impressive detail of structures like this in the brain. And this is data taken at 7 Tesla in a live, human brain. Remarkable pictures. Okay, so that's that. Let's go to, I think I have the next one on here. Yeah, good. Okay. We're gonna do this. Okay, good. So let's just review quickly. Here's our basic pulse sequence, okay, where we have the 90. Magnetization goes down into the transverse plane, starts to precess in the transverse plane, causing this free induction decay. Because of magnetic field differences from point to point in the patient, the signal decays more rapidly than T2, which is this envelope. So you can apply a 180-degree pulse to cause a spin echo and image that thing. The T1 recovery is from 0 back to its equilibrium value. T2 is from whatever value you have right after your RF pulse, where you've taken your magnetization vector, put it in the transverse plane, and then it decays away in the transverse plane with a time constant. And here's a review of that pulse sequence where we have a slice encoding gradient, a phase encoding gradient, and then a readout gradient to sample the Fourier transform of the object. This is actual raw data. Kx is this direction, ky is this direction. And let's recall what the gradient fields are doing. So we have a static magnetic field at, let's say, 1.5 Tesla or 3 Tesla. And then if I switch on an X gradient, a Y gradient, and a Z gradient all simultaneously, let's say I switch them on, and it's going to change the magnetic field as a function of position. And the amplitude of the gradient times the distance in X will give you the frequency change from the X gradient, and the same for these as well. And so switching these gradients on and off is what's used to do the encoding. I don't know if this is the best way to do it in a short term. So let's try. So here's our signal as a function of time. And that signal, again, is this thing, right? Here's our signal as a function of time, okay? So S of t is this thing. And it's here. And the way S of t is generated is we have magnetization vectors. Let's just do it in one slice. We won't take Z into account. We have magnetization vectors in the XY plane. And so M will be the sort of amplitude of the magnetization vector at position XY. The frequency that magnetization vector is processing at is dependent on the gx value times x and the gy value times y. And so for any time t, say we switch this gradient as a function of t, all we have to do is integrate up how much, frequency difference was there during the application of that gradient pulse. And so from 0 to time t, we have a gradient on, you multiply by whatever your x position is for the magnetization, the y gradient multiplied by its y position, and you integrate that, right? And that will give you essentially because this is a frequency shift, right? When you integrate it, it gives you a net phase shift for the magnetization at x and y, okay? And this can be rewritten if you define kx and ky, which are, remember, the Fourier components in the x direction and the Fourier components in the y direction. So this is in cycles per meter, I guess spatial frequency. With this definition, right, you can rewrite this equation such that it looks like this. And now it kind of makes a ton of sense what's going on, in the sense that as a function of t, right, for the integration from 0 to some function of t, you are essentially changing the kx value, right, as that function of t, and you're changing the ky value as that function of t. And so what this is doing is just, if I have my kx in this direction, ky in this direction, this function here is just moving kx and ky through that space. If I drop ky, let's just drop ky for a second and just say, well, how does kx work? Remember, as a function of t, we just went across. The gradient was on as a constant value, And what we were doing was we were moving across the Fourier transform and changing the kx value as a function of t. So it's called a, basically a k-space trajectory. When you pulse a gradient in terms of the x gradient, when I turn it on with some amplitude and integrate it from 0 to t, I wind up at a kx value at t, right? And similarly for y. And so the gradients can control our position in k-space, right, for sampling of the object and the position of Fourier space. So I'm not going to do that one though. So here's a very interesting pulse sequence where we have an RF pulse and it has a slice selection. Okay, so now we have selected a slice of the patient here. And what I'm going to do is, while I am acquiring my data, okay, I will oscillate both the, let's call this the x gradient and this the y gradient. So I'm going to oscillate the x gradient back and forth, right? And change its amplitude. Its amplitude's going to grow. And I'm going to oscillate the y gradient back and forth, right? And what that does is it puts me on a trajectory. I start at the middle and it spirals. Oops, oh shoot. And it basically spirals us out in k-space like this as that oscillation occurs, right? And while that's occurring, I basically sample voltages from the, my receiver coil and record that signal. And when I put that recorded signal back into the plane like this, I generate the Fourier transform of the object. Another example would be, I take a radio frequency pulse, make magnetization vector in the transverse plane from a selected slice, and then I pre-phase it and then read out constantly. And so what this is my readout here. So what happens is I put my magnetization in the transverse plane here. I pre-phase, so I go down to this location, right? Because I'm moving, with a kx and a ky is changing with t. And then I turn around and go in the opposite direction. So I sample across here, right? And then stop. And then I will do that whole thing again, but I change these amplitudes such that now I'll move to this line here, and then the next one I'll move to this one here. The next one I'll move to this one. And so in that way, using a sequence of these pulses and gradient pulses, I can map out the Fourier transform of the object along these rays. This obviously looks a heck of a lot like CT, right? And in fact, it is. And this was probably the first way magnetic resonance imaging was done, was with this type of trajectory, and then using existing CT reconstruction algorithms to reconstruct this. For cardiac acquisitions, here's our k-space or the Fourier transform of the object. What can be done is you can take a recording of the ECG of the patient, and then you can decide, I'm going to make a picture of this part of the ECG right here, say this 100 milliseconds right in here. And what we can do is we can, in that time, sample as much as possible of the k-space. So maybe I have 1, 2, 3, 4 pulses. So 1, 2, 3, 4 pulses along here. And for each pulse, I will do a phase encoding gradient to get me up to this row and then read out. And then the next pulse, I'll do a different phase encoding gradient to get me up to this row and then read that out. And then the next RF pulse, I'll do a phase encode to get me here and read that out. And so I do that 4 times inside this green zone, and I put that into my Fourier transform. And then on the next heartbeat, I will do it again, but use different phase encoding pulses so that I map to a new location in K-space. And then on the next heartbeat, I'll do it again, but again, different phase encoding pulses. So now I fill in this part of the K-space. So this is called, a segmented acquisition, in that we're acquiring, in this case, 1/3 of the data from this beat, 1/3 from this beat, and 1/3 from this beat. Now, most of the time you can't do it in groups of 3 because, you can't get enough Fourier data just with these 12 acquisitions. You need maybe 64 or 32 acquisitions. So you're going to need more heartbeats, right? And oftentimes, as we saw with those really nice pictures, there were examples, it takes, say, 12 heartbeats, and you can build up enough K-space data over 12 beats to get a really nice picture. Now, we do this same process for every other window here as well, right? And we do that all at the same time. So we get a movie of the whole heartbeat. If we want to do our acquisition in fewer heartbeats, we can do a set of phase encoding pulses such that we get a bigger chunk of time. We step through a whole bunch of phase encoding pulses here and call that one segment. If I step through half as many phase encoding pulses and call that one segment, I need twice as many views or twice as many heartbeats to fill in my K-space. But when I reconstruct, I have higher temporal resolution because it only represents this, time window here. So there's a trade-off. If I have to do this in 4 heartbeats, maybe I, do a very large window and just make fewer, essentially frames in my movie. But if the patient can really hold their breath, for a long time, say 32 heartbeats, maybe I can do like 3 here and I get 96 total phase encoding pulses per time frame. Also, you can do what's called view sharing, in which you take the first part, the last half of this time frame and the first half of this time frame, combine those together to make a new time frame. So if you sequence these appropriately, you can generate time frames that are in between these two. Fundamentally, the temporal resolution, I wouldn't say, it doesn't go up by a factor of 2 when you do this, because there is this view, it's view sharing, right? So you're smoothing between views. However, it can make the movie interpolate sort of more smoothly. We looked at that example. We looked at these. Okay, so contrast from different pulse sequences. The spin echo pulse sequence. So this is all the same patient, same slice, right? And so in the spin echo pulse sequence, because of this dark blood contrast, where the blood that was in this slice has gone by the time the 180-degree focusing pulse is used, you get these voids where blood is. However, you get very bright signal from fat. Fat has a short T1, so it recovers magnetization quickly, and it has a relatively long T2, and so it looks quite bright on these spin echo images. In a gradient echo image, and that means we're not doing a spin echo, we're just going to make pictures from that FID. Do I have a picture of that somewhere? So a gradient echo image is like this, where we do an RF pulse in a slice and we just read it out right away. We don't do a spin echo. And then we do that again in a short period of time, right? So that's a gradient echo image. And it looks something like this, right? So you get bright blood in all chambers. The signal to noise of this sequence is usually lower. However, the acquisition time for this can be quite short. The acquisition time for this is usually not short. It's in like tens of seconds to a minute or something like that. Acquisition here can be down to a few seconds, right? And then these are sequences in which the radio frequency pulses here are brought very close together. And that's why we need these gradients to switch at such high rates. Remember, we talked about switching from here to 50 millitesla per meter over here in about 250 microseconds, right? So you want these ramps where you're not sampling to be as short as possible. The issue with making them any shorter than they are now is that you start to stimulate neurological activity and nerve activity, peripheral nerve activity in the patient. Let me rephrase. I don't think you stimulate neurological activity, but you stimulate peripheral nerve firing. And so you can feel like a twinge, and involuntary motions and things like that when you switch really fast. So you don't want to do that. So we bring this as close as possible. And if you, instead of using these small tip angles where you read out just a small bit of the magnetization, use a large tip angle, you can kind of get a steady state of these, what is essentially a train of different echoes. And they turn out to be fairly bright. It turns out to be a very efficient way to get a lot of signal. And you get a picture that looks like this. So again, we're back to the bright fat. Here we've got very bright blood because new magnetization is flowing into the slice. And we have very bright signal on long T2 tissues such as cerebral spinal fluid that are surrounding, this is the spinal cord here, and this is the thecal sac. Look on the spin echo, that was a very dark signal because its T1's really long. Here, it's very bright signal in these steady state acquisitions. So this is just 3 of probably 20 different acquisitions that you can choose to look at the heart. And I would say this is principally used the most because it's the most robust, and you get high signal to noise pictures in a fairly efficient way. What are you going to do here? Oh, okay. So here, we're at 43. Okay, we'll do this application because it's pretty important. It turns out that MR is really good at measuring when a tissue has an infarct in it. And so let me just show you one of the pictures first. So if you look at this MR picture here, that bright signal right there, which is patently obvious. I mean, you don't have to be a rocket scientist to go, hey, this is abnormal. That is retention of contrast agent after injection, say 10 minutes after the injection, in tissue that has gone on to be infarcted or dead tissue. The contrast agent gets in there and it takes a very long time to come out. And so you get these what are called gadolinium late enhancement images. And it's one of the things that sets MR apart from every other imaging technique is that you can get these super high resolution pictures of infarcts. And when we look at it, so here's the blood pool after injection of, this is time in this direction, and we're going to inject gadolinium contrast. It's called gadolinium DTPA, and it's injected in a vein, just like CT contrast. And the signal in the blood pool goes up precipitously. It has high contrast, and then it decays away as the contrast sort of goes out into the kidneys, etc. And then the normal myocardium, obviously it gets enhanced, not as much as the blood, but it also decays away like this. And then the interesting thing is the infarct, it takes a longer time to enhance. So there is a time in which normal myocardium is brighter than the infarct, but then at some later time point, it basically is shining brightly and the rest of the heart is back down to normal. And so this is like at 10 minutes, right? And so this is the classic gadolinium late enhancement, or GLE imaging. The source of the contrast is the fact that in the infarct or scar, the contrast agent has been retained, and so the T1 of the tissue, when it's got that contrast agent, is short. And so that means that when you take most MR pulse sequences, if you have a short T1, the tissue will look bright because it recovers very quickly. And so here's the T1 curve of the infarct with the scar in it and the contrast, and here's the normal myocardium at that 10-minute time point. And you could make a picture where the normal myocardium actually has 0 signal, right? And then the infarct has positive signal. But this was done a lot, this 0 nulling thing. People would find the time where the normal myocardium was nulled, and I think it was silly because you have all of this signal difference all along here. You shouldn't have to hit this point exactly. You can make a picture where you have a difference from here to here, and it's going to be just as good. And the problem is, if you get to a point, say here, and you reconstruct the image with magnitude reconstruction, so that if you don't look at the phase and you see the normal myocardium is actually negative, when you do the reconstruction, it comes to the same contrast as your infarct. And so you kind of wasted everybody's time. And you get a picture where you have normal myocardium coming back up positive. The infarct here is still quite positive, but the contrast between it and the background is not as good as it is over here, right? So anyway, that's a case for saying, hey, you should retain the phase information of all of your voxels, all of your magnetization vectors, so that if they're negative, you can display them as negative, right? And then here we see basically a late enhancement. There's let's see, what is this phase? Oh yeah, so this is where you can plot the normal myocardium as negative and the infarct as positive, and you get much better contrast between the two. Okay. The other thing that has been done is you can essentially integrate up the infarct volume and see if that is a predictive parameter for somebody's outcome. And as you might imagine, if your infarct is big and it encompasses, say, half of your heart, your prognosis is not as good as if it is a smaller infarct. But the interesting thing is, if you have a heart attack, and you've had a heart attack, say you had ECG changes, etc., and they get in and they fix it and they put a stent in, you can go to MR and you get one of these pictures and see how much normal tissue do I have left. Am I like right on the precipice, like half my heart's gone? Should I really start working out my paperwork? Or is it a small infarct, right? And then even a more sophisticated thing is, like, given an infarct of a certain geometry or size, what is the propensity of that shape, that position, that size to generate electrical arrhythmia? Because that's the thing that's going to kill you, right? Is you're going to generate some kind of ventricular tachycardia that will evolve into VFib, right? And so predicting that is probably quite valuable, because you could, in those people that have much higher risk of generating arrhythmia, you could put a defibrillator in them, for example. Okay, and so here's you can measure the evolution of your injury. And so this is 1 week after this person had a heart attack. And you can see that there's chunks of tissue where there's obviously gadolinium retention. There's tissue where the contrast isn't even getting in, right? So it's still dark. And then, after it's stabilized and the infarct is fibrotic and everything, it has a different appearance, right? You can see how that evolution is going. Okay, I'm going to quit there. Okay, and we'll take up some more examples on Monday. So I think we have 2 lectures left, basically. We got Monday and Wednesday next week, and we'll I'll try and get my X-ray stuff done next week so that we can have 2 full presentation classes, so you're not time constrained. Because I think the projects, I was really impressed with the project proposals, and also in my mind, you're going to need a bit of time. Those projects are pretty ambitious, and so I'd really like to spend a good amount of time, talking together as a class and everything like that on the projects. And so that'll probably be the last 2 lectures. Okay, of the week after next. Okay, any questions today on today's lecture? We'll take this, pick this up here on Monday.
Yeah, that sounds good. Thank you.
Okay, great.